So I forgot to start recording at the beginning of the lesson. We'll pick up right here. We are modeling this situation with a polynomial function. We have already listed all of our possible rational roots. We found that 2 was actually 1, and we're left with this, which translates to this quadratic, which makes us a little sad because if the 3 and 4 switch places, it would factor, but right where they are, it doesn't. And so since it doesn't factor, how would we find our other roots?
It doesn't.
Quadratic.
We would use quadratic equation. So it would be negative b plus or minus the square root of b squared minus 4ac all over 2a. And then we notice that we get a negative 7 under the radical, which tells me it's what kind of imaginary. Okay, so we have some complex imaginary roots right here. So if we're talking about real life, will these complex roots work?
No.
No. So our only rational solution is 2, which is our only real solution. So it's only our only possibility for w. So we know the width is 2. So since we know the width is 2, and that is 2 meters, we can come up with the dimensions of this box. This box should be a 2 by 4 by 1 meter container. Those are our dimensions. Does that make sense?
Because it's a double.
Yeah, I just plugged it in. 2, 4, 1.
You can't
Oh,
spell.
my mind's gone.
Okay.
I just thought I tried width with a D.
It does have a D, but it's in the middle.
No, I meant I tried to spell it. Starting with a D.
All right. Now, example 1 that is not in your workbook of our additional examples. This says a farmer has 1,600 feet of fencing and wants to fence off a rectangular field that borders a straight river. So here we have a river and it has a straight edge to it. There we go.
How?
I just drew it, see?
No, but
All right.
everyone that would never have.
Well, it might. I'm sure
So he
somewhere.
needs fencing. He needs no fencing along the river. So we're creating some kind of rectangular-ish field right here against the river. No fencing necessary over there. River.
That's cool.
Okay? So what are the dimensions of the field that has the largest area? And that's all we have. That's all the information we have. So we have to work with what we have.
We have nothing.
We have nothing.
You could.
Okay. So what could?
You should be finding a vertex.
You might, wait, that is a possibility, but how do we know if that option of taking 1,600 and divided by 3, because I have 3 sides, will give me the largest area? It'll give me an answer. All right, what are you thinking?
Should you be finding a vertex and asking for a maximum?
Yes! That is exactly where we're headed with it. You just made my heart happy. All right, so how do we get to that point? Okay? So, we don't know this, and we don't know that. Okay, what do you think, Brock?
Okay, so since perimeter equals, do you want to go with the river's length or width?
Doesn't matter to me.
Okay, well we'll make it a length then.
Okay, so he makes the river the length.
So you would set perimeter equal to L plus 2W. Right? And then area equal to L times W.
Okay, so those are important concepts.
So,
But we have too many variables.
oh no,
Yeah, you did.
We have too many.
so,
It is upsetting. Okay, I'm about to do one little sneaky thing, and that's it, and it's going to be enough for you guys.
Okay.
The reason it's enough for you guys is because I'm going to call the width x.
Oh, yeah.
That's enough. What's the other width? X.
I said X. What was the X?
No, it's a rectangle. It's a rectangle, so opposite sides are congruent.
couldn't do 16 divided by this class.
Yeah, because we don't have 4 sides, we just have 3.
I got that right.
Okay? Now, yes, this length here would be 1600 minus 2x. That is the most it possibly could be. Does that make sense?
So that's the equation?
Okay, so what equation are we going to work with? We've got the picture. We named some stuff. Are we going with this or are we going with this? What are we trying to maximize? Area. So let's go with area. Area is equal to the length times the width, which, if we were to distribute, gives us 1600x minus 2x squared, which actually takes us right back to last year when we fell in love with the quadratic. Okay? So this is a quadratic function, and what Brock said earlier, if we're looking for the largest area, we are looking for the maximum.
How did you know that?
This is a parabola that opens down. And the vertex of a parabola is always the... Yes! Yes! X equals negative b over 2a
Class are we in?
I don't know.
is how we find the x value at the vertex of a parabola.
Rock seems to get used.
Negative b over 2a.
That part
Okay?
makes sense.
Now, okay, let's say you couldn't remember any of that. Let's go with what we learned this year. In factored form, don't you know that one of the intercepts is at 0, 0?
Right.
Where's the other one?
2 times 16.
What would this x value be?
You're asking me if that's
I'm asking everyone.
1600
What would
zero.
what would make that? What x value?
16.
What x value? Gotta double it.
Zero. Okay, keep it going. Say it.
4.
800.
800 because you want the same value.
Okay. So I've got this at 800. And do you guys remember last year from graphing quadratics that the vertex is always halfway in between your x-intercepts?
Is that why we do parabola and the height?
Yeah.
Okay.
Okay, so what if we do negative b over 2a, which is negative 1600 over 2 times negative 2, which gives me 400.
Wait, what?
Or,
Okay.
if we go back to the fact that we know the vertex is located halfway in between the two x-intercepts, which would be 400. Either way, we get that the value for this dimension, which would maximize the area,
Okay, so that makes more sense.
that would give us the biggest area, the top of that curve is the biggest area, is 400. What's my unit? Feet. So if this is 400, then what is my other dimension? 800. So the dimensions of that rectangular field are 400 by 800 feet.
That is a Death is knocking on my doorstep.
Knock, knock, knock.
Okay, I'm recording, by the way.
That's a good song, huh?
It's great. Okay,
It's a good song.
I'm not arguing. Number 2. Just reminding you, I am recording. All right, number 2. A company needs you to design a box
Great.
with no top from a square piece of cardboard. And while we all laugh about making a box, side note, I never thought cardboard boxes were that exciting. Until my friend that I graduated from tech with got a job at a company where he made boxes. That same friend got promoted quickly through the company.
Is he like CEO of a box company?
He's a multi-millionaire at this point.
What? For box?
Has retired
It's
from
like the guy
making
moving in the
boxes,
pool noodle.
and at this point works for fun.
Oh my.
So,
Works for fun.
yeah.
That's crazy. He makes boxes and he gets millions of dollars.
He used to make, he moved on. He does consulting now when he wants to.
Okay.
When he wants to. When he wants to. You got enough money, you don't have to work all the time. Alright. So, here we go.
My stomach is like,
Let's take a look at this highly entertaining and profitable box making business. Alright. So, I mean, I laugh too. I don't laugh now when he posts that Facebook video every Christmas of his new toy. Yes.
oh my god.
Every year, brand new one.
Yeah, I'd be mad too.
Yep. Alright, and I keep coming to work to teach.
But you love us, though.
I do love y'all. I win.
Let's
That's
not.
right. You're right. I
I
win.
was still as honest.
Okay. A company needs you to design a box. This box has no top. Okay, that makes it really easy. We don't even have to think about the top. The company wants the height to be 3 inches and the volume to be 432 cubic inches.
Okay.
Alright, so here we are. We're starting off with this nice square piece of cardboard. And we're going to take this cardboard and create a box. For those of you that have not made cardboard boxes before, the simplest way to do this is to just cut out some little squares from the edges. And then you can fold up the sides. See if I fold right here, and I fold right here, and I fold right here, and I fold right here. After cutting out this, and cutting out that,
Do you work with your
and
friend?
cutting out that,
She made
and
multi-millions
cutting out
in
that.
secrecy.
You see how that would create a box. Okay, so that's what we're doing here, folks. Pretty simple, pretty basic box building.
Wait, why did you draw it back?
Well, because we need it for a second.
I make pen.
Alright, so we want the height to be 3 inches. So do you see when I fold this, the height comes from right here and right here. So this little part and that little part have to be 3, right? Okay, so that's 3, that's 3. And to keep my box from being cattywampus, I'll make them all 3.
I like that word.
Alright, look it up if you need to later. Alright, that's all I got. And I know I need volume. And we already talked about volume misleading times width times height of a rectangular box. Yes, sir.
Would it be 3 times x minus 6 squared?
It certainly is.
Yay!
Okay? So, because we do not know this dimension, we have to use a variable. X is my favorite. But this is really the dimension that matters, because that becomes the length when I cut this and this out.
So we wait.
So if all the way across is x, this would be x minus 6, because 3 and 3. Well, it's a square. So the other dimension would also be, yes. Okay, so that's where the x minus 6 and the x minus 6 and the 3 came from. And we want this volume to be 432. Alright, I'm always about the easiest way to solve something. So, I'm not going to do more work than I have to if I see it. And I see it. This times this is that squared. And when I divide by 3, a very beautiful thing happens.
140.
It is 144. And then there was rejoicing in the room because 144 is a perfect square and we can take the square root. Now, we are using common sense here. And even though we know when we take a square root we get plus or minus, in this case minus is dumb. because that would end up giving us a negative dimension, which would mean it doesn't exist. So we're going with only positive. So x is 18. So what size cardboard would we need? We would need an 18 by 18 inch square of cardboard in order to create our box. What would the dimensions of the box be?
Second, you said the question?
3 times.
What was your question?
What would the dimensions of the box be? This is the cardboard. 12 by 12 by 3. Very good. The cardboard is 18 by 18. The dimensions of the box that we would create with the cardboard would be 12 by 12 by 3.
Why did it in a different way?
Alright, any questions?
This one.
Not yet.
Oh no.
One more together.
I don't understand how.
Because I all hope that you'll be multimillionaire box makers one day. Let's do one more.
I'm gonna come back and say, Miss Willoughby taught me this.
That's right. Okay, so number 3. An open box is to be made from a rectangular material. We left the square. We've moved up in the world. This rectangle is only 15 by 9 centimeters. We're going to cut squares out of the corners to turn up the sides to create our box. Visual people like a picture. Let's draw one.
I'm gonna smack.
All right. Once again, we are still recording.
Oh jeez. She said, once again, we're still recording. I just said, I'm gonna smack you.
Yeah, she did.
We're live recording.
All right, so we know that all the way across is 15 and all the way across here is 9, but when we create the box,
Do we still cut out like 3 by 3?
Well, we don't know.
we don't know. And when we don't know, what do we use?
X.
X. So what are we cutting out?
X.
2 X's. An X right here and an X right there. All right, so what would this dimension be when I cut it out and fold it into a box?
9 minus 2x.
9 minus 2X. And what would the height be?
What?
Just X. So the volume is going to be X times 9 minus 2X times 15 minus 2X. Okay, this is not a quadratic. It's cubic. It's a higher degree polynomial function. We've studied the cubic. The leading coefficient, positive or negative? Positive. So we know the ends are going like this. Oh yeah.
Wait,
It's going like this. The ends are going like that. All right, and we also know the zeros. What are the zeros of this function? Right now. 0, yeah.
0,
4.5
and 7.5.
and 7.5. Very good. So if I had to sketch it, which I don't have to, but if I did, I'd just sketch 0, 1, 2, 3, 4, 5, halfway in between. 6, 7, 8, halfway in between. Zoop. Woo. There we go. All right, there's my quick little sketch. Now, let's talk about reality. X represents a dimension. X represents the height in this case. And a height, can it be negative? No. Can it be 0?
Yes.
No.
Oh, no.
No. If it were 0, it wouldn't exist.
Wait.
Okay? So X represents the height. So when I'm thinking about X, that's really thinking about the domain. When I'm thinking about possible X values for this function, I'm thinking about the domain. We just ruled out negative X values, and we just ruled out 0.
So 1, wait.
Would 1 work? Yeah, it could. Okay, so I know I can start at 0. Where does that end?
Infinity.
Where does the end? Okay. If I won't go as far as infinity, but let's say I plugged in 100.
Long ways.
Heights would be good. Whoa. If I plugged in 100 here, do you see I get a negative dimension?
Oh.
Oh,
And
anything
a negative
within the
dimension.
roots?
That won't work.
Okay.
So that domain has to be restricted. It only works for positive values because we're talking about a measure, something I measure, a length, a dimension. So where do you think it stops?
Where the roots are?
Okay.
Or of the positive. the roots.
Okay.
Also, the maximum.
So where do you think it would put you? You're right.
4. Well, I was like, yeah, 4.
4.5.
5, yeah, it has.
4.5. Can it equal 4.5?
No.
No. Because at that point, we have just made this dimension 0. So, the only valid answers for this problem lie in between 0 and 4.5. Algebraically, could we get more answers? Yes. Would they be right? No. Okay. Now let's move on to part B. Find the values of x such that the volume actually equals 56. Now, if we had this typed into our calculator, we could do a second equation. Y equals 56 and see where they intersect, couldn't we? Or we can do like we did on the first problem. If we set this equal to 56 right here for volume and subtract it from the end, what does that do with the whole graph? Shifts it down. And the reason it shifts it down is it takes that line we're looking at and moves it down to the x-axis. Why is that helpful?
It puts the domain below positive, so the box can't be moved. I don't know.
Well, at that point, we can use our calculator to just find our zeros. Because we have shifted it to where that graph now intersects the x-axis at the points where the volume is 56. That's what subtracting 56 from the end does. It causes a vertical translation down to where all we're looking at is the zeros of the graph. All right, so what we're going to do now is we're going to look at it on our calculator. We know we want this to equal 56, and when we move that 56, we are forcing this graph to shift down so that the answers to this question are the zeros well, this is an equation, so it would be the roots of this equation. The answers to this become the roots of that. All right, calculators.
Wait.
Oh, Jesus. Oh, is that 8?
All right, let's zoom 6 so we can get a pretty picture.
I got 6. I mean 8.
Oh, that's not pretty.
No, it's not.
That's pretty ugly.
8 works.
Okay, 8 is a 0, but does 8 fall in your reasonable domain? No. So, in context of this problem, is 8 a solution? No, it's not.
Oh, it says
I see 2 answers though. I see this one And I see this one.
Can't we use synthetic division to add A?
We could, but we don't need to because we have our technology. We can actually find the zeros. Now, I'm going to change my window because I don't want to see this extra stuff that I know is not part of the solution. So I'm going to hit window. I know my reasonable domain is from 0 to 4.5. So I'm going to make it go from -1 to 5. That way I can see everything that's important. And I could tell that maximum was really high. Could y'all tell it went up pretty high? So I'm going to make that like 100. Maybe that'll be good enough. Let's see. Graph. Okay, I can see the maximum. I never answered the question of part A. We talked about it, set it up, never answered it. We'll come back to that in a second. And I can see my zeros. How do I find my zeros?
Trace and.
Nope. From the video last week. Second, trace. And then choice 2. Go to the left side. Enter. The right side. Enter. And enter for guess. My first 0 is 0.5. I'm just going to go ahead and tell you the second 0 is actually 3.5.
I knew it.
And then I'm going to go backwards to the last question because I oopsed and got excited about part B and never answered part A. Okay, so we know the answers were 0.5. The next one is actually 3.5, guys. And then 8 was the last one that Julian saw first, and we decided it's a 0, but it's not an answer.
So is it physically impossible?
So that's the impossible one. These two will work. Now, I forgot to answer this question. I set it up, we talked about it, we said, hey, it's got to be that maximum. Maximum, maximum. It is the maximum that occurs in this window. So let's go back to our calculator real quick and just get rid of the -56. Let's go back to our calculator and eliminate the -56, and we can find that maximum.
Oh, whoa.
Going back to my calculator and just deleting
I can't go to it, Jesus.
the 56.
Oh, there we go. That makes sense, right?
Now, if I want to find the maximum, it's up here. Mine's slightly off my screen. No biggie. I don't have to see it to find it. But I'm trying to find a maximum, so I second trace this time. Choice 4. Go to the left side of it. See if I can't even find my blinky. Do you guys see how you can tell where you are at the bottom of the screen? So I know where I am, I just don't see my cursor blinking yet. Oh, there it is. It made the screen. Do y'all see it now? Okay, I know I'm on the left side. I hit enter. I go right till it shows back up on the right side. There I am. There I am. I see me. I hit enter. And so it gives me the maximum, and this is what I should have talked to you about first. So that is what I use to answer that top part. There it is. So I know that maximum, and this goes with part A. That goes with part A before I had the 56. That maximum occurs at an X value right here. So my dimensions would be 1.82 by 9 minus 2 times 1.82. That gives me 5.36 by 11.36. Sophia rocks out on the other side of
It's pretty hard to make a box.
Alright, there we go.
I don't. Well, I mean, it's technically the same.
Okay.
Let's see.
So your homework's out of the workbook. Some word problems. And you have 10 minutes. Okay, no, you have 6 minutes of class time, so you